Good afternoon, my name is Jorge Pey and I am going to present this work entitled Geochemistry and Sources of North African Dust Results from the Donaire Aerosol Deposition Network in Southwestern Europe. This work has been done in collaboration with my colleagues from different Spanish institutions and it was supported by the POSAPI. Dust from North Africa is emitted all around the north of the continent, but the source areas can be grouped in 6 potential source areas according to the work published by Steuben et al. 2013. In these areas, we can look at different geochemical ratios, for example, sodium versus aluminium, or calcium plus magnesium versus iron, or potassium versus aluminium. And if we look at these ratios, we can observe a slight or important variations among the different potential source areas. And these variations are strongly related with the geological composition of the materials presented in the north of the continent. According to this work published by Moreno et al. In 2006, they collect different samples all around the North Africa and in most cases very close to the major emission areas, and they observe that the differences in the composition are very important among these areas. For example, Western Saharan dust are more carbonate in composition and with hematite and mafic clays, including palygorskite, and these sediments are depleted in titanium. On the contrary, the chat basin dust are more related to primary mafic minerals with a simple felsic composition, and mostly these particles are clays and quartz, and we can encounter some diatoms. And finally, the agar massive dust are relatively rich in insoluble major elements, including sodium, potassium, calcium, or magnesium, and they are related with the erosion of ancient granitoids in this region. So for this study, we built a network that is made of 15 sites, including regional background, industrial, urban, or agricultural sites, and this is located in Spain and in the Balearic Islands. And the aims and objectives of this study is to characterize the phenomenology of Saharan dust inputs in this region and to constrain the geochemical variations associated to African dust, and finally to separate the dust sources if possible by means of a receptor model. So the methodology for this study is composed by the collection of samples every 2 weeks in the 15 sites. Then we go to the lab and we filter the samples by means of a filtration ramp, and with this process we obtain 2 different samples. One is a liquid sample, and we use for the determination of anions and cations by means of ionic chromatography, but also the soluble heavy metals by means of ICP-MS. And in the filters, in the insoluble fraction, we determine the concentration of organic and elemental carbon by means of a thermo-optical analyzer, and we digest part of the filter to obtain the concentration of major and trace elements. So another step in the methodology is the dust calculation. So for this end, we use a very simplified approach, so which is based on the identification of the periods in which dust fall occur, and this was done by means of the observation of aerosol maps or direct observation of the samples. Then we remove these periods for the calculation of the average deposition flux, and with this we can estimate the background flux without having the influence of Saharan dust. And finally we can obtain dust fall out by subtraction from this theoretical background the actual concentrations. And this approach has been used also for individual chemical species. So the deposition fluxes at the regional background size has been used as the reference ones for the identification of the main dust deposition episodes, and this has been done in different regional background areas. For example, we observed a very big one episode affecting the northeastern part of Spain in October 2016, another one in November 2016, a third one in February affecting different parts of the network in February 2017, and finally we select a summer episode in June-July 2017. So regarding the first episode, the one occurred in October 2017, so this, according to the meteorological situation, which was a low pressure system in the southwestern part of Portugal, we observed that could be a mix of source areas affecting the northeastern part of the Iberian Peninsula. So the second episode affected severely the Ebro Valley and the Pyrenees, and in this case, this was a single potential source area responsible of this gas transfer. So the third episode had a very similar meteorological scenario as the one occurring in November, but in this case, the main areas affected was the Pyrenees and the southern part of Spain, and also it was related to a single source area. And finally, the fourth episode registered moderate to low concentrations in terms of deposition, but the sources in North Africa were very mixed, especially when compared with the other. So regarding the geochemical ratios, we can start with the first episode occurring in October, and we can focus our eyes on this part which was the most affected in terms of the position, and we can see that the variation of these four geochemical relations is very narrow. For example, the iron titanium is around 1112, or the sodium aluminum is around 0.065. So we can keep these numbers and we go to the next, which was a strong, which was a very strong one, and this affected all this part in Spain. So we can see again the numbers of these markers, and we can see that the iron titanium is very different from the previous one. Is in this case is around 22, 27, and then the previous was around 10, and also the sodium aluminum was very different. It's around 45, 50, and the previous was 65, and the others has also have also differences with respect to the previous one. So the third episode, the one occurring in February, was mainly affecting these two parts of Iberia, and in this one the concentrations were very high also in the south, and the ranges for these four relations are very similar to the presented for the November episode. And finally, the summer episode was a very homogeneous distribution in terms of the position, and again the relations for these four markers are akin to the ones presented for the October episode. So in summary, the geochemical ratios that we obtain for our study are varying in these ranges presented here, and the next step that we are going to to follow is to use these ranges in combination with other proxies, including magnetic or isotopic analysis, for the exploration of the dust encountered in paleo archives. And you can see the presentations by Valero, Garcés, and in this conference. So the next step that we run is the source apportionment by means of positive matrix factorization, and only we include in the analysis the samples affected by dust from North Africa, and these are the samples related to the fourth episode that I mentioned in this presentation, but there are other less important episodes that are included in this analysis. So after running the model, we encounter a total of 10 factors or sources. Two of them are related to African dust sources, another one with regional dust, and we find also the marine, traffic, regional pollution, three industrial sources, and another source that is very well related to coal and fuel burning. So in this first case, again we should remind that affected mainly in this part. So the contribution of the two African dust sources is dominant. As you can see here, the traffic source in Barcelona is much more important than in Montseny, that is the regional background. And we can see that the African 2 source, which is the intense yellow, is more important than the African 1. So in this second episode, that, if you remember, affected especially this part, again the African sources are the main contributors to the total aerosol load, but in this case the African 1 source is the dominant in this episode. So the third episode, the one occurred in February, again the African dust was the main source, especially here and here, but we can see that there are differences. In the south of Iberia, the African 2 source was the dominant, and on the contrary, in the north it was the African 1 source, the dominant one. And finally, the summer episode, which has moderate concentrations, so you can see that the relevance of African sources is not as important as in the previous episodes, but still we can see that only the African 2 source is present in all sites, and only small parts of the African 1 can be seen. So in conclusion, we have measured the aerosol deposition and the dust deposition at 15 sites in Spain. We have studied the geochemical signatures during dust episodes, and we can say that these signatures are rather uniform among the sites. And this is telling us that our results are really robust. We have found that there are some geochemical ratios that are interesting for us, and especially the iron titanium or potassium aluminium or iron aluminium, while some others are not so important because they are strongly disturbed by local contributions, and this is the case for the ratio calcium plus magnesium versus iron. So the sources encountered during dust events are diverse, but PMF is able to separate two African dust sources apart, another source that is corresponding to regional dust. Regarding the African sources, the first one is strongly related to northwestern African dust sources, while the second one can be interpreted as a mixture of dust sources without a clear origin. So these two sources occur mixed, and they appear frequently together in our study. And we have observed that the African one source, which is related to the northwestern African dust, is not dominant in summer when most of the African dust episodes occur, but when this source is encountered, is usually related to very intense African dust deposition events. So this source emerged as the main potential source in the next step in the project, which is related to paleodust archive study. So thank you for your attention, and if you have any question, I will be more than glad to answer you in the specific session.
Thank you very much, Jorge. If you have questions, please send them in on the chat session if you're not there, or if Jorge, if there are people in the audience wanting to ask questions, you can probably see them and ask them to ask the question directly to you.
Okay, if there is someone with some specific questions, you can send me an email, or I can reply right now.
Jorge, I have a question for you. If you, is there any evidence that this dust is going past the Pyrenees into the Gulf of Biscay? Is there a deposition of this African dust further to the northwest, do you think?
For sure that there is some deposition upwards of the Pyrenees, but one thing that we are going to do is how much the dust is deposited in a transit from the south to the north of the Pyrenees, because our hypothesis is that most of this dust is deposited in the south part of the chain, but for sure that there is dust blowing northwards, and there is deposition.
Thank you. Are there any other questions? We have time for one more question if there is one. I don't see any on the chat, so. Okay, thank you very much, Jorge.
Thank you.
So our next speaker is Sonia Castillo, and she's going to speak about quantifying depositional fluxes in 2 national parks with contrasting African dust influence.
Hello, my name is Sonia Castillo, and I'm a researcher from the Andalusian Institute for Air System Research, belonging to the University of Granada in Spain. I'm going to present you the study titled Quantifying Deposition Fluxes in 2 national parks with contrasting African dust influence, the north and the south of the Iberian Peninsula. This study belongs to the project POSAPI. In this project, we study the Saharan dust influence in the Iberian Peninsula and in the Balearic Islands. In this project was designed a network of sampling stations to collect bulk atmospheric deposition in different locations in the Iberian Peninsula. Here you can see the different stations. The stations are concentrated in the northeast of the Iberian Peninsula, in the Balearic Island, and in the south. Why is important this network for the study of the African dust? Because as you can see here, we have the situation of the dust belt in the world, and in this imagine of the Tom's aerosol index value, we can see that the Sahara Desert is the higher emitter of dust to the atmosphere in the world, and close to this big desert it's located the Iberian Peninsula, our place of study. Here you can see the situation of the desert with respect to the Iberian Peninsula, and the frequency of these episodes in the Iberian Peninsula is really high. We have also 4 scenarios under the dust air masses can travel to the Iberian Peninsula. These scenarios have different synoptic meteorological situations, and here you can see these 4 scenarios. Where is he? Okay. Here you can see the 4 scenarios. The first scenario is the North African height at surface levels. In this case, we have an anticyclone over the South Iberia or North Africa. The dust air mass travel through the Ocean Atlantic. This air mass travel normally at surface levels, and this type of episodes are short and normally from January to March. The other scenario is the Atlantic Depression. In this case, we have a low in the Atlantic Ocean near Portugal. The dust comes from the western part of the Sahara Desert, and normally these episodes are related to rain. So the frequency of these episodes are wet episodes. Other situation is the North African Depression. In this case, we have a low in North Africa over Morocco or Tunisia, and in this case the dust mass is travel through the Mediterranean to the Iberian Peninsula. These episodes are normally also associated with rain. Finally, we have the most frequent scenario over the Iberian Peninsula, the North African height at upper level. In this case, we have a high anticyclone in the Argelia, over Argelia. We have intense heating of the Sahara soil, because these episodes are normally in the warmer month, in summer normally. And we have a transport of this dust from the Central Sahara to the north. With this situation, the objective of our study is to identify the contribution of North African dust episodes in the atmospheric deposition in 2 locations at different distance from the Sahara Desert and with distinct climate context. So, if we have here the map of our study area, in the Iberian Peninsula we select 2 national parks in the network. Here you have the network of the national parks in Spain. We select 2 national parks with different distance from the Sahara Desert, with different climatic contexts, to study the different possible influence of the dust from the Sahara. In this case, we select at the north of the Iberian Peninsula the Ordesa Monte Perdido National Park, and in the south of the Iberian Peninsula the Sierra Nevada National Park. Here you can see a topographic profile of the Iberian Peninsula. Here you have the Sahara Desert. Close to the Sahara Desert you have Sierra Nevada mountains with our station, and distance from the Sahara Desert. In the north of the Iberian Peninsula you have the Ordesa Monte Perdido National Park. The altitude of our station are higher in Sierra Nevada to 1,550 meters, and in Ordesa Monte Perdido the altitude is 1,190 meters. This is our stations, the station of Ordesa Monte Perdido with the bulk atmospheric deposition collector, and the station of Sierra Nevada with the dry and wet atmospheric deposition collector. This is the idyllic situation, but the normal situation when we go to collect the samples is this, with amount of snow. We collect the sample. In the lab, we make the filtration process to separate the insoluble fraction from the soluble fraction. The insoluble fraction is deposited in these filters of quartz fibre filters, and these filters with the soluble dissolution, it's analyzed in the laboratory. With the insoluble filters we make acid digestion, and with the soluble part we make the analytical process to analyze around 60 parameters, 60 species per sample. In the case of the insoluble fraction, we analyze the major elements, the trace elements, and the carbonaceous species. In the case of the soluble fraction, we analyze the soluble ions and cations. In this study, we are going only to present the soluble fraction, because we are waiting to some analysis of the insoluble fraction. So in this study we are going only to present this part. Okay, so we start showing the annual deposition at both stations. Here you can see the 2 years of sampling period, from November 17 to October 18, and from November 18 to August 19 at both sites. Differences in the precipitation. In Ordesa Monte Perdido is similar, but in Sierra Nevada depends of the year. No, if you have drier years, you have less precipitation than other years. In this case, we can see that in these 2 really different places, with different distance from the Sahara Desert, with different climate. Remember, the Ordesa Monte Perdido have a humid climate, whereas the Sierra Nevada mountains have an arid climate. So all through this situation, we can see that the total deposition, the bulk deposition in grains per area, it's similar at the two places, really similar. The differences comes when we separate the insoluble and the soluble fraction. In this case, in the humid station, in the humid location, we can see that the dominant fraction is the soluble fraction, and in the arid station or location, we can see that is the insoluble fraction the dominant fraction. The same situation we have in the daily fluxes. In the daily fluxes, we can see also we present the milligrams per area per day. That is similar at the two stations, but the differences comes in the soluble and insoluble fraction. That these results are the expected, no? Because in a humid place we have more time to have soluble ions than in more arid places. Here we take our stations at other national parks in Spain from the north and from the south. In this case, we represent the highest number of samples recorded under dry conditions. Okay, so we have here the percentage of sample under dry conditions and the latitude. And as we can see, these stations are all in the north of the Iberian Peninsula, and these stations are in the south. We can see here that the stations in the south have a higher percentage of samples under dry deposition because we have arid conditions here. Here we can see the bulk deposition registered in the different seasons along the study period in Ordesa, Monte Perdido and Sierra Nevada national parks. We can see that the periods where the bulk deposition is high are the hottest period, the spring and summer, and the periods when we have the lower bulk deposition is the colder months. Okay. In this situation, we can see a heavy spring in 18, both in Ordesa, Monte Perdido and Sierra Nevada national parks, and big differences in the spring and summer of the 19th. In this case, we can observe the amounts of dust of bulk deposition in Sierra Nevada mountains with respect the Ordesa and Monte Perdido. These two seasons, spring and summer of 19, were seasons with several African dust episodes with notable influence in the south of the Iberian Peninsula. This is the same situation, but with the insoluble and the soluble fractions. Here you can see a similar situation where the soluble fractions is the dominant fraction in the colder months, and the insoluble fraction is the dominant fraction in the hottest months. The same situation we have in the daily fluxes. Daily fluxes are similar at both places, with the unique difference of this last summer of the study the study period. If we represent the annual mean species contribution showing the principal emission sources and species, we can see that in Ordesa Monte Perdido, the mineral source is a very important source in this area, and the carbonates, the species with the carbonate species. So the soil influence in this area is really important. When we have under the North African episodes in this place, we can see that the dominance of the carbonates it's increased in a few orders of magnitude. The mineral is also the secondary, the second important source in this area. But in the case of the south of Sierra Nevada, the principal source in the annual mean contribution is the marine source. In this case, not only represent the marine contribution from the Mediterranean or the Atlantic Ocean. In this case, also represent the salts in the soils. Also, in Sierra Nevada, similar contribution have the mineral source and the sulfate species. When we have in this area the North African events, we can see the increase of the mineral soil, of the mineral source, and the carbonates. We can see better this situation comparing the both places. Here we can see the not expected amount of mineral and carbonates species to the total mean contribution. Not expected because the position of the stations makes that in a common sense the station in the south near the Africa desert with more higher frequency of those episodes register lower dust deposition than the location in the north. In the north, with a distance from the Sahara Desert, and here we can see that the mineral contribution during the North African episodes in the north is really important, and is more than the 50%. Is around the 70% of the total amount of mineral species in this station. The same situation is for the carbonates. The carbonates are higher with respect to the carbonates registered in Sierra Nevada, and with an important contribution when we have the North African episodes. So, in the south of the Iberian Peninsula, we have around the 35% of the days under North African conditions. Here you can see the line of the samples during the study period. We can see here the peaks of heavy African episodes. Here we have a really heavy episode, and also other normal situation in the south that is during a few months. Normally in the summer, we have continuous fluxes of African dust to the south of the Iberian Peninsula. You can see here this period with the dominance of the insoluble fraction. What we have when we have these peaks, these heavy episodes in the south, we can have days with this visibility. Here you can see this is in a location in the south of our station at sea level, and you can see here the situation with days with heavy African dust episodes. In the other part, in the north, as you can see here, we don't have the same situation. We can see here peaks representing heavy or heavy or not heavy African episodes, and the rest of the time we have normal levels. These heavy peaks can reproduce these situations. Here you can see a really heavy African dust episode. Here you can see the pink snow. This is snow in Ordesa, Monte Perdido. And if we compare the lines, the evolution of Ordesa, Monte Perdido with the evolution of Sierra Nevada mountains, we can see these differences. No, we have more normal levels during the year, along the year in Ordesa, Monte Perdido, and broken with these heavy peaks representing heavy African dust episodes. But in the south we have other situation. We have also peaks with heavy episodes, but we have also periods with continuous fluxes from the desert. So we can conclude in this study that bulk atmospheric deposition at two national parks with different geographical location with respect to the Sahara Desert have been analyzed, whereas similar bulk deposition fluxes have been observed at both sites. It is observed important differences in the soluble and insoluble fraction. These differences are mainly related to the number of wet deposition events, frequent in the north, in the Ordesa Monte Perdido, and scarce in Sierra Nevada. In Ordesa Monte Perdido, the soluble fraction is the dominant fraction, with a contribution to the total deposition around the 65%, whereas in Sierra Nevada, is on the contrary, the insoluble fraction is the dominant fraction, and this fraction contributes to the total deposition around 65%. In Ordesa Monte Perdido, carbonates increased notably during the North African events, whereas in Sierra Nevada, not only carbonates but also the species, typical species from soils, experiment also a notable increase. Although higher impact of dust are registered in the south, remember the 35%, the dust deposition is higher in the north. Several NAF events in Sierra Nevada account for less amount of dust than the observed in Ordesa Monte Perdido, which is controlled by one of two only severe dust deposition episodes per year. So, we can conclude. Could be the possibility that the Pyrenees act as a natural barrier of dusty air masses traveling to the north, creating the knowledge foehn effect. Thanks for your attention.
Okay, thank you very much for that very nice talk, Sonia. Are there any questions there in the audience? I see no questions on the chat. Sonia, I have a quick question. In the photo you showed with all the dust on the snow, does that lead to melting events?
Hi, it's not Sonia talking, but it's Jorge Pey again.
Oh, okay.
My colleague is today. She is a little bit sick and she cannot connect. Answering your question, so this is one of the research line that we have, and I can tell you that yes, actually the dust episode in 2018 that Sonia has shown in the presentation, the snow was melt around 2 weeks before than the expected.
Wow. Okay. Thank you very much.
You're welcome.
Okay, let's move on if we can to our third speaker, who is Anika Rohde, and she's going to speak about the impacts of snow darkening due to Sierra dust during an intense dust deposition event across Eurasia.
Okay, thank you for the introduction. I hope you can all hear me all right. I'm a fresh postdoc at the KIT in Germany. And I will talk about the impact of snow darkening due to mineral dust deposition on the optical properties of snow. And Pavla already mentioned this, and also in the last presentation we saw some pictures. But in my research, I'm using the model IconArt to investigate this impact, and I improved the model to account for this snow darkening effect in the model. And I will show you some results from a case study which I did for my PhD thesis. And this opening slide shows a picture which was taken in the Alps. And I hope you can see the orange patches in the snow because they are caused by mineral dust particles. And with this, I'm at the motivation of this research. So why do we care for a few mineral dust particles in the snow? So there are many regions where we can have very high mineral dust concentration in the snow. And also in Europe, we have a couple of times where Saharan dust is transported to Europe and can be deposited on snow surfaces. And also this year was a very great opportunity to observe this phenomenon. And for this is here a satellite picture. This was shot on the 6th of February this year. And you can see quite clearly the transport of Saharan dust to Europe. And the mineral dust particles also deposited on the snow surfaces, as you can see from this photo here. This was taken in Switzerland. And you can see how severe this orange color is in the snow. So this coloring of the snow, this is the snow darkening, and this leads to an enhanced absorption of solar energy, and this leads to snow melting. And to give you one example how severe this can be, here's a figure from a paper from Skiles and Painter from 2019. They simulated a snow cover during springtime, and they took some measurements of mineral dust concentrations, and the result is here on the upper figure on the right-hand side. But they did also a reference simulation where they assumed clean snow, and this is the figure on the bottom. And when you compare those two simulations, then you can see that the snow cover disappears much earlier in springtime. They found an advanced snow melt by 30 days. So the impact can be quite large, and it can decide if we have a snow cover in springtime or not. And before I get to the simulations, I would like to say a few words on the optical properties of snow, which are important to understand this phenomenon. So here are shown figures from Skies et al. From 2018, and what you can see is the spectral snow albedo. So the albedo of snow in the different wavelengths. And the albedo is the ratio of scattered to incident shortwave radiation. And from all three figures here, you can tell that the snow albedo is very high in the shorter wavelengths, so the snow is highly reflective. But when we go towards the near-infrared range, then the snow is more absorbing. So here are shown two important aspects. So when we start on the left-hand side, we can see the impact of light-absorbing impurities in the snow. So light-absorbing impurities, these are the aerosols, and you can see the concentration here. So with higher concentration of these aerosols, we get a lower snow albedo, and this is mainly affecting the visible range. Then next to it, there's also another important feature which has an impact on the snow albedo, and this is the snow aging, or also called snow metamorphism. We can characterize the age of the snow by the snow grain size, because when we have fresh snow, then these snow grains are very small, and then they grow with time and the scatter properties change. So this dark blue color here shows you old snow, and we get a lower snow albedo for old snow, and this is mainly affecting the near-infrared range. So we can tell from these figures now that we need to consider both these processes, so the aerosols in the snow as well as the aging of the snow, if we want to simulate the spectral snow albedo. So I will say a few words about the model that I use. I already mentioned that I work with ICAN-ART. So ICAN was developed by the DWD, the German Weather Service, and the Max Planck Institute. And the weather forecast in Germany is calculated with this, but the model can also be used for climate simulation. A special feature of this model is that it consists of a spherical icosahedron, so we have a triangular grid, which makes the model seamless. We can run it on global scale, but we can have also a very high resolution on regional scale. Then there's the ART extension. So this extension was developed at the KIT in our working group. And this module calculates the aerosol process. So we have included sea salt, volcanic ash, mineral dust, and other traces. ART does the online emission, transport, also some interactions of aerosols and the deposition. We also include optical properties for several aerosols. So I would like to explain to you the aspects that I implemented during my PhD thesis to investigate this impact. As I mentioned, the aging of the snow is very important, so I introduced a new prognostic variable, the snow grain size, to account for the age of the snow. I also implemented the Mi coefficients depending on these grain sizes. And then I also implemented a parameterization for the spectral snow albedo, and this is based on the theories of Wiscombe and Warren. I use a multi-layer snow model. So I also introduced the stratification of aerosols, so we can have different aerosol concentrations between the snow layers, and when the snow melts, then the aerosols can resurface again. And last but not least, I also implemented then the interaction of the optical properties of snow and mineral dust. So with this, I'm getting to the case study that I did, and for the investigation of the impact of the mineral dust particles, I picked out a very special event that happened in 2018. So here, Saharan dust was transported to Eastern Europe and also Western parts of Asia. And hopefully you can see here on the satellite picture on the right-hand side that we have a very big difference between dusty snow and clean snow. But also this photo above the satellite picture here was taken on the same event, but a little bit further to the east. This was taken in Georgia. And also here you can see how severe this event was. So I took this opportunity to do some simulations with ICAN-ART. I generated an ensemble with a total of 80 simulations to get a more robust result. And I simulated 10 days of this event from March 22nd at a horizontal resolution of 10 kilometers. And here on the right corner, you can see the simulation domain and two areas which I marked here with A and B, where I looked a little bit more closer to it because A contains the Caucasus mountain range and B contains a more flat area. But there's the snow line inside of this square because there's the border between snow-covered and snow-free surfaces. So this slide here shows a small validation of the simulated mineral dust transport to satellite measurements. So for this, I took measurements from the Calliope LiDAR from the Calypso satellite, and I took 2 dates to compare. So on the left-hand side, you can see the 22nd of March, and on the right-hand side, the 23rd of March. So at the top, you can see a small map with the flight path of Calypso. And then here, down here at the bottom, you can see the comparison between the LiDAR measurements and our simulation. So you can see here the attenuated backscatter. And on the top, the Calypso measurements. And here comes the tricky part because in the measurements, we have different inferences from different aerosols and also clouds. And these clouds are often a problem because they disguise the aerosols, so you cannot see below the clouds here. This is what you can see on the left-hand side. Where we really get a view of the aerosols is between those white dashed lines. So this is the emission area, the source. And here we can see a lot of mineral dust in the measurements, but also in the simulation. But when we look more north, above 30 degrees north, then we cannot see below the clouds, but in the simulation result on the bottom, we can see that the mineral dust is transported to Europe more northwards. And what is also really interesting is when you look at the cloud top in the measurements and top of the dust plume here, then you can see that there are very similar patterns. So we can assume that these mineral dust particles travel in the clouds and also below the clouds. On the right-hand side, so on the 23rd of March, we have a very similar situation. We have a lot of clouds, unfortunately, but also here the patterns match very nicely. What we can see in the simulation results is the deposition in our study area, which we cannot see, unfortunately, in the measurements. So with this, I get to the simulation results, and I'm showing you some horizontal distributions on a specific point of time after 176 hours of simulation, so about 1 week after simulation start. The reason is that there the feedback was at the strongest, and you can see 2 different variables here. On the left-hand side, you can see the dust deposition. And on the right-hand side, you can see the feedback in the surface albedo. So blue color shows you a decrease in the surface albedo due to mineral dust particles, and red shows you an increase in the surface albedo. It is also important to mention here that I applied a snow mask. So where you see only white color, there's no snow, because we're not interested in that. So on the left-hand side, you can see the deposition. And really interesting is that we see the mountain ranges. We can see, for example, the Alps. We have a lot of deposition there, but we can also see very clearly the Caucasus mountain range. And on the right-hand side, when you look at the feedbacks, we can see that we get a strong feedback in the eastern part of this map and also in the Caucasus Mountains. What is also very interesting is that we get a strong feedback here at the snow line in Kazakhstan. And this is a more flat area, but we get a really strong signal here as well. You can see that on the right-hand side, we have also an increase in the surface albedo despite mineral dust deposition. And we found that a little bit contradictory. So we applied a statistical significance test to see is this result also statistically significant. And I can tell you that we looked at many variables and we found that these increases in surface albedo is mainly caused by random changes in precipitation patterns and also cloud patterns. And now I will show you only the statistical significant results of the surface albedo change due to mineral dust. And as you can see, the reduction in the albedo is mainly significant. And also here again, we can see the Caucasus Mountain and we can see the area along the snow line. Here I would like to show you a few feedbacks in other variables. So the relationship to the changes in the surface albedo. So these are density plots. So how often specific relationships occur in the simulation domain. And these are only the significant results. So on the x-axis, you have the changes in surface albedo due to mineral dust particles. On the y-axis, you have several other variables. So on the left-hand side, the surface shortwave net flux, on the middle, snow depth, and on the right-hand side, the surface temperature. And you can see that there are different relationships. So on the left-hand side, the surface shortwave net flux has a very linear relationship with the change in the albedo. We find also a quite linear relationship between the changes in snow depth and the albedo. You can see that we have found here a correlation coefficient of 0.76. So with a decrease in the surface albedo, we also get a decrease in snow depth. But on the right-hand side, you can see the surface temperature compared to the changes in surface albedo, and this is not a linear relationship. You can see that there are many other influences on the surface temperature, and we cannot directly derive the changes in surface temperature with the changes in the albedo. Here I would like to show you that there are regional dependencies of the feedbacks to mineral dust deposition. So again, here is the change in surface albedo, but I would like to show you a little bit more closer the feedbacks. So in this region A, where the Caucasus Mountains are, we find a strong feedback in snow depth. So we have a significant reduction in snow depth of minus 1.36 centimeters after 1 week. And when we look at another region, this region B here, which is a more flat area, here we get a much more stronger signal in the surface temperature. So we have here a warming of about 1 Kelvin. And the difference between these two regions is that in A we have complex terrain, we have a closed snow cover and deep snow, whereas we have in B a flat area where the snow line, so we have a very thin snow layer, so we get much more impact on the ground below the snow. So with this, I'm at my conclusions. So I showed you that we found different significant impacts to mineral dust deposition on snow. So we found significant reduction in the albedo and the snow depth. Also a significant increase in surface shortwave net flux and surface temperature. But we didn't find any significant impact on clouds and precipitation in that short time. I also want to emphasize again that there are two different vulnerable regions. So we have the complex terrain. Here we get mainly a reduction in snow depth. And then there's the area with the snow line. Here we get a strong signal in the surface temperature. And with this, I'm at the end. And thank you for your attention. And I'm looking forward to your questions.
Thank you very much, Anika, for a very nice talk. I see no questions on the chat. Are there any questions there in the audience? Oh. I have a question for you then.
We have here also a question.
Oh, I'm sorry? You have a question there?
Yeah.
Okay.
So thank you for the nice talk. My question is actually the difference that you show with the albedo, with the dust deposition. How is this compared to the deposition, for instance, of black carbon?
I mean, it depends on the position. I mean, if you just compare black carbon and mineral dust, then black carbon has a stronger impact. But of course, there are regions where we have more black carbon or more mineral dust. Yeah, sometimes, just because of the abundance of mineral dust, the impact is stronger. So it depends on the region, really.
My question relates to your last series of slides and your conclusions that in the mountainous area, the dust actually caused melt, but in the flatter areas, you've got temperature changes. Do you want to speculate on why that is?
So I mentioned that we have a very thin snow layer. We have also snow melt there, but we have we see a stronger impact in the surface temperature because when the snow melts away, then the ground below the snow is uncovered, and then we get a more impact also on surface temperature because the surface heats up. And also when we have a thin snow layer, then also it's not optically thick, so we get also an impact on the ground below. Does this answer your question, or?
Yes, it does. Thank you.
Okay.
And thank you very much for your presentation.
Thank you.
So let's move on to our fourth talk, is by Federica Bruschi, and she's going to speak about the chemical and physical characterization of seasonal snowpack at the Calderone Glacier in Italy.
Students in chemical sciences in the University of Valero. And today I'm going to present our work concerning the glacier we are writing is located on the Garcés in the Union, and you can see it on the map on the right. There is a process which is considered as part of the Garcés. I will talk about the second side later. The glacier is lying
I'm sorry.
Sì, condividi prima lo schermo.
Ok.
E fai partire la tua. No, devi fare uscire.
Eccolo qua.
Togli questo.
Dov'è?
E vai sul cartellaggio. Ok, la 4.
Ok.
Good afternoon, everyone. My name is Federica Bruschi, and I am a PhD student in chemical sciences in the University of Perugia. And today I'm going to present our work concerning the Calderone Glacier. The glacier we are analyzing is located on the Gran Sasso complex in the Apennine area, and you can see it on the map on the right. I also want to ask you to notice the other site highlighted in the map that is called Monte Martano, which is 200 kilometers far from the Gran Sasso mountain. I will talk about this second site later, so please try to keep it in mind. The glacier is in a valley below the Corno Grande, between 2,700 and 2,900 meters on the sea level. The Calderone Glacier is at present the most southern glacier in Europe, and it has been giving a very quick response both to short and long-term climatic variations, which resulted in a considerable reduction in surface area and volume. In fact, it experienced a loss of surface area around 50% and of thickness about 65%. That's also why it has been split into glacierets since the early 2000s. Since early 90s, the Calderone Glacier has been subjected to several multidisciplinary field campaigns to monitor and evaluate its role as an environmental indicator of the global warming. To monitor the glacier itself, Professor Pecci have always calculated the mass balance, while the rest of the monitoring concerned mainly the snowpack. A physical monitoring has been carried out with both classical geomorphologic methods in situ and remote sensing techniques. Moreover, the chemical composition of the fresh snowpack was also investigated. In fact, from 2008, the PAH, the major ions, and the paraffins were quantified, while from 2013, the elementary and organic carbon analysis was also added. In the last few years, we started to analyze also the trace elements with a high spatial resolution, and lately we also tested a new method to quantify the rare earths. The sampling is usually organized 2 times per year, in particular at the beginning and at the end of the ablation season. Unfortunately, in the last few years, the sampling campaign in September was not always successful, since, as I said, the glacier is definitely loss-making. However, the campaign consists in digging the snow pit and, after measuring the physical properties, such as densities and temperature, taking the different samples with a different spatial resolution depending on the analytes. More samples were also taken from water sources located under the glacier at different altitudes. The analysis used to investigate the chemical composition of the snowpack were ion chromatography and inductively coupled plasma mass spectrometry, employing, in this case, an instrument with a triple quadruple and a collision reaction cell. The analytes that were included in the analysis method are listed in the slide. With the ion chromatography, it was possible to see the main inorganic soluble ions, since the concentration of the organic ones was always too low to be detected by this instrument. On the contrary, with the new ICP-MS, it was possible to go down to concentrations around the ppt for many of these metals. During this work, I focused on the data of the past 4 years, and particularly on the results obtained with the ICP-MS. The snowpack, as you all know, is a passive sampler of aerosol from the atmosphere, and that means that looking at the stratigraphy and comparing it with the chemical composition, it is possible to reconstruct atmospheric events that led to a strong deposition. In this graph are described the snowpack profiles obtained with the aluminum fluxes for the last 4 years. All of these peaks were noticed also with many other metals, but I chose aluminium since it can be considered a marker of crustal particulate. You will notice that there are many peaks highlighted, and that's because they all match with atmospheric events that were recorded in our station located on Monte Martano, the site that I showed before on the map, and that can be also considered far from anthropogenic pollution. The usefulness of this atmospheric station on Monte Martano is that almost every perturbation and advection arriving at the Gran Sasso area at some point will also be seen there. In the Monte Martano site, there are 2 particulate matter sampler and an OPC. We can compare now the OPC data for the year 2020 with the relative aluminium profiles. The 3 peaks that you can see in the snow correspond, in fact, to the peaks given by the increased number of particles in the atmosphere at the end of March, in April, and in May. Depending on the air masses circulation, many different advection can reach our area. The most common source, though, is always the Saharan Desert. In this graph, you can see the vertical profile of the flux of iron, a marker for Saharan advection, that was quantified in the fresh snowpack found in June 2020. As we notice with the aluminium, there are 3 distinguished peaks for 3 different advections. Using specific programs, it was possible to figure out the specific region where this dust came from and in which amount. In this case, the peak located around 250 centimeters deep was a weak Saharan advection that took place in April, while the higher peak, around 115 centimeters deep, is a stronger Saharan event that arrived in May. Looking at the circulation data, though, the third peak does not depend on a Saharan advection. However, nowadays, new dust sources are becoming more and more relevant. One of these is the Caspian region. In this particulate area, in fact, as it is noticeable from the images, a new dust source has been created in the last decade. In fact, the Aral Sea, that's very close to the Caspian one, is now drying out because of the agriculture and loss in vegetation. Using the data collected from the Monte Martano site to calculate some back trajectories with high split for the events of last year, we noticed that in late March there was an incursion of dust in Italy coming from the Caspian region. The graphs that you're looking at are relative to 2 consecutive days, and on the second one, the light blue trajectory comes from that region. Moreover, in the lower part of the second image, you may also notice that at first the altitude of the air mass was really low, so it was loaded in crustal particles, and that's why the peak in the snowpack was really intense. Since the provenance of this advection is different, we decided to investigate them from a chemical point of view in order to find a specific marker. To better address the differences between the two events, both snow from the Calderone Glacier and filters from the Monte Martano sampler were analyzed. Since we saw iron fluxes before, let's see who is the iron associated with. In this plot, it has been considered together with the silica, and both are normalized for the aluminium. In this graph, the darker dots in blue, red, and yellow, with the sampling date on it, describe the aerosol filters sampled on Monte Martano, while the lighter ones, also in pale blue, red, and yellow, represent the layers of snow in which we found the higher fluxes, and therefore that we connected to the atmospheric events. The white dots instead stands just for snow layers without any particular dust load. You may notice, looking at this plot, that there is a first separation between the values of the Caspian dust and the Saharan dust, while the snow samples seem quite homogeneous. Focusing on the dust, it catches the eye that the 2 days in which the maximum amount of PM10 was registered during Caspian advections, that are the one circled in orange on the left, have a very low silica to aluminium ratio, but for the moment it was not possible to explain why. In the snow, it is impossible to see these differences as a consequence of the debris local contribution and on the deposition and post-deposition processes that they may have been. In this plot, the issues with the snow samples are even more clear, as the layer containing the Caspian advection is the one with a lower sulfur to aluminium ratio, while the respective dust has the higher one. Since the sampling has been done when the snowpack was already starting its ablation, it is probable that the sulfates were already shifting to the bottom layer, and this is also confirmed by the ion chromatography values, since in the first 3 meters from the top of the fresh snowpack, the sulfates always resulted lower than 0.2 ppm, that was our detection limit. Moreover, it is clear that there was a local contribution looking at the 2 red dots in the right side of the plot. They seem, in fact, enriched in calcium compared to the respective dust, and we know that the limestone and the clays present around the glacier have a calcium to aluminium ratio respectively equal to 390 and 190. Looking at the aerosol samples instead, there is a clear separation between the 2 series, probably due to the fact that in the Caspian area, as reported in literature, there is a high amount of salts and gypsum. These advections, as anticipated, were also investigated for rare earths. Turns out that in this particular case, this cannot be used as marker to assess the sources, since there aren't important differences in the patterns. This tells us that the silicate species were similar between the events, but lower in concentrations in the case of the Caspian advection. Actually, looking at the first part of the pattern from lanthanum to neodymium, we can notice that the two Saharan advections are different one from the other. They probably came from different areas, and the one was more silicatic of the other. Anyhow, we can see from this graph that changing the matrix does not affect the patterns too much, even though the concentrations in the snow are definitely lower. In order to investigate advections on snow and compare them with an active aerosol sampler, the method must definitely be modified. First of all, a sampling campaign should be added to collect the advection right after the deposition in order to minimize the local contribution and to avoid the displacement of the chemical species in the snow. That said, in the specific case of the Caspian advection that we saw in 2020, it would be useful to deepen our knowledge about its geochemistry of the Caspian area, in particular this silica-aluminium ratio that we didn't understand yet. So, for the moment, thank you for your kind attention.
Thank you very much. I note that you're on the participation list. Are you able to answer questions?
Yes,
Federica?
yes, absolutely. Hi.
Hi, very nice talk. Thank you.
Thank you for the opportunity.
Are there any questions there in the audience? I see none on the chat. I will go ahead and ask one then, if that's okay.
Yes, absolutely.
As you pointed out, you've got the concentration of the light rare earths are very, very high in the dust. Do you have any idea if that's related to a specific rock type, or do you think those are rare earth elements that are absorbed onto iron hydroxide, or what are your thoughts on the source?
Oh, well, the thing is that I don't really know if they are from a particular kind of rock, because I don't know whether the two Saharan advections and the Caspian one have actually the same composition. So I don't know if I can actually say that. About the concentration, if that was the topic of your question, I think that the difference can probably be due to the fact that the aerosol samples were taken with an active sampler. So we had a pump taking a lot of aerosol into a filter. So it was actually probably more concentrated than the one that we found in the snow, since it was a passive sampler. So maybe that's the reason why the concentration are so different. But maybe, as I was saying, there's also the melting of the snow that, let's say, worsen the situation.
Yeah, so you're saying that maybe some of the lighter rare earths were lost as the snow melted. It dissolved the phase or whatever it's controlling their composition, right?
Mm-hmm.
Okay, that's great. So are there any other questions? Again, I see none on the chat. Okay, thank you very much again for a very nice talk. Let's move on. Sure. I'm going to turn it over to my colleague, Ann Carey here, and she's going to introduce the last two presentations.
Our fifth presentation of this session is about urban soil formation in a case study in Moscow, and it will be presented by Tatiana Prokofeva, and we look forward to hearing her talk.
Chiudi.
Non esce.
No,
Non esce dalla presentazione.
condividi. Hai condiviso? Prego, condividi. Fai scena.
Screen.
Sì, no. Devi andare su.
Macino.
Sì, vai. Falla partire. Ok.
Dear colleagues, I am glad to participate in the DUST conference. I would like to present a report, Solid Atmospheric Fallouts as a Substrate for Urban Soil Formation, case study in Moscow. Authors. My colleague Sergei Shoba and I, we are soil scientists. And the third co-author is Vasily Shishkov. He is an expert in electron microscoping. The process of airborne dust deposition connects soils with atmosphere and other components of the city environment. Solid atmospheric fallouts are usually mentioned by ecologists in the context of pollution assessment. However, such fallouts from the atmosphere actually include very diverse solid components that are deposited on the surface of soils. So we can consider a solid atmospheric aerosol as a substrate for soil formation. Our long-term study on the composition of solid atmospheric fallouts was conducted over a set of summer seasons in the city of Moscow. There were mainly the places of our soil research. Moscow is situated in the central part of Eastern European plain, folded by loose sediments. It's in the southern taiga natural zone with humid temperate climate and percolate soil moisture regime. The average annual wind speed is 2.3 meters per second. The street dust has been studied. Airborne dust deposits studied within recreational and roadside zone were sampled into plastic containers, but by direct precipitation. Dust samples in places of accumulation on urban road and construction structures were also collected. Morphological and chemical properties of dust and soil was examined with microscopes, a binocular microscope and polarizing microscope, and a scanning electron microscope with the energy dispersive spectrometer. We used soil analysis methods for dust because both dust and soil have a silicate matrix. It was revealed that dust deposition intensity significantly varied between different study areas. Mean dust deposition rates at our study sites varied from 10 to 50 grams per meter square per year. Such broadly corresponded to the overall mean in Moscow, 33 grams per meter square per year. Dust deposition rate in Moscow region is 2.5 grams per square per meter square per year. The studied dust samples were generally similar in the composition with abundant quantities of macroscopic particles of building materials, especially in samples taken near buildings. Dust aggregates with salt cementation, microplastic, textile and plastic fibers fungal geyfer, and fragments of feces were common in samples from different study areas. The dust amount deposited on soil surface is not large. However, dust adds not only silicate minerals, but some specific components, metals, black carbon, and others. The spectre only shows elements with relatively high total concentration, more than 1%. Some dust units consist of salts, a large amount of carbon, sulfur, and chlorine give us evidence of chlorides, sulfates, and carbonates presence. Fragments of mortar and plastic fibers are usual in atmospheric dust. We found feces in the dust of both recreational areas which we study and at the roadside sites. Dust deposits within recreational zones were enriched in organic residues, pollen grains, and aeroplankton organisms. Roadside dust deposits also included asphalt concrete particles and thin films of hydrocarbons. We consider dust as an important substrate for urban soil formation. In our soil studies, we identify a special diagnostic horizon for urban soils. Its name is urbic horizons. Its chemical composition is very similar to street dust. According to our previous study, diagnostic horizons of urban soils developed as a result of pedogenic transformation of different substrates simultaneously with the surface deposition of these materials, including airborne solids. You can see fresh infiltration of street dust in the pores inside the upper horizon of the urban soil, red arrows. Dust is very important for urban soils as it enriches them with alkaline components, carbon and pollutants. Dust, together with additions of other substrates, provides a gradual upward growth of surface soil horizons. We suppose that not only construction waste, but small inclusions from the atmospheric fallouts provide the common geochemical properties of urban soils. Microscopic artifacts found in dust samples very similar to common microartifacts in urbic horizons. For example, microfragments of limestone are found both in samples of street dust and in the soil in the neighborhood. This picture shows the red asphalt cover. During the Soviet Union time, the area around the university, Moscow State University, was covered with a special red asphalt with high amount of lead and chromium. Now we find fragments of this road cover both in the dust and in the soil around the university. Thus, solid atmospheric fallouts contribute low quantities but a high diversity of materials in the upper horizons of urban soils. The composition of airborne dust includes air plankton, pollutants, particles of building materials, and other alkaline substances. Deposition of airborne dust can result in such soil properties as high contents of hydrocarbons, heavy metals, and high content of organic matter, and also neutral and alkaline pH, and so on. Apparently, solid precipitation provides the direction of soil evolution towards the geochemical homogeneity of all modern urban soils within the city. Atmospheric dust is a very important part of urban soils. Thank you very much for your attention.
Thank you for that. Thank you for that nice presentation. I haven't seen any questions in the chat. Are there any questions from the audience? Well, while you're thinking, I was interested if any of the locations in the city are used for growing vegetable gardens, or just thinking about the heavy metals that you analyzed.
No, we didn't analyze heavy metals in kitchen gardens, but inside Moscow, there are many locations with high amount of heavy metals. It's due to aerial deposition. It's normal for urban environment. And Moscow is a very, very high megapolis. So we have not much amount of kitchen gardens. But the apples from University Botanical Garden is not so dangerous. It's okay. But I think it's the matter of the properties of apple trees. And I have one question
I see.
From chat.
Yes.
There is a question in the audience. Maybe I can interrupt, or maybe there's a question in the chat, but I will raise my question. The characterization that you've made is how long after the deposition of the particles? Because I guess that to create a soil, all the deposited particles have to be processed and transformed and, I don't know, metabolized by microorganisms, I don't know. So did you characterize on long term the depositions and how to turn from atmospheric deposit to a soil?
Sorry, I'm not understand completely. I am looking at the chat.
Okay,
sorry.
You can maybe answer the chat question, and then I will try to make my...
Chat question is how long was the sample collection? It's thank you for the question. The periods of dry seasons in Moscow is not very long. Actually, the period is not long too. A period of now our collection of our samples is not too. We use 1 month in the summer. It's usually August month. usually in August. August is most not most dry, but very useful for the dust collecting. And we have also dry March, but there is a snowy snow cover inside Moscow. During the March, we collected, we are collecting, collect samples from the road constructions. And also we collect some dust samples from the road construction during the August and September.
Okay, thank you. I think you have indirectly answered to my question.
Thank you very much.
Thank you, Tatiana. Very interesting talk. We probably ought to move on to the last talk of the session. The next speaker is Blas, Valero, Garcés, and the talk is another one about Saharan dust deposition in this time in peat bogs.
Good afternoon. I would like to introduce you a little bit about our research in the Pyrenees, trying to look for Holocene archives of Saharan dust deposition. This is a collaborative work between different researchers and institutions in Spain within the umbrella of the POSHAPI project. So during the last, actually in the last year, there have been quite a few events that they seemed that they had been a little bit more intense than in the past with Saharan dust deposition during the winter, even in the mountains with incredible landscapes as the one that you see there in the Central Pyrenees in the last February. So it seems that at least the popular perception is that these dust events are increasing. And this is one of the motivations of the POSHAPI project, trying to understand the current or the more recent dust events in the Iberian Peninsula, but also trying to understand what happened in the past. And to do that, we used a network of sites and kind of a paleolimnological approach, trying to find the best possible sites that they may have some indicators that they are relatively easy to explain in terms of dust deposition. Two of them is the one that we're presenting here. One of them is the Arshui pit bog in the Western Pyrenees, and the other one is Marboret Lake, high altitude over 2,600 meters elevation in the Central Pyrenees. The Arshui pit bog will recover 4.5 meter sediment and did all the new age model and new analysis. And in Marboret Lake, we've been working on that particular lake for almost for the last decade. So this is some of the results, these preliminary results, trying to identify these periods of higher dust deposition. In this kind of general screen, we use iron to titanium ratio because the dust, Saharan dust is highly enriched in iron. So in these two graphs, you can see how the upper part in Arshui, the last 2,000 years, is the one that they have the highest ratio, and in Marboret is the last 4,000 years with some peaks in the mid-Holocene too. So in general, the picture is similar to other sites with early Holocene stability, increasing dust during the late Holocene and after what is after the end of the African humid period, and particularly in the last millennium. If we look into a little bit more of higher resolution, then and the Marboret are the ICP data and Arshui's XRF data. But it seems that there's a higher dust input during warmer and arid phases, like the current period, post-Isolate, medieval climate anomaly, the Iberian Roman period, kind of in both places, in both sites are, that's kind of the picture that emerged from this preliminary study. In general, within the Iberian Peninsula, there are different patterns. In the northwestern part of the Iberian Peninsula, some records point more to periods of negative North Atlantic oscillation, kind of colder water periods, periods with higher dust. In the central part of Spain, it seems that positive North Atlantic oscillation periods, warmer, are the ones they have higher dust index. In some speleothem records, it seems that more intense westerly periods that they're associated colder periods are the ones that they have higher dust input. So it's not at all a clear picture all over Spain, but we think that these two particular records are very promising. So looking ahead, we're going to get new geochemical indexes. Going to study in detail the mineralogy, also the magnetic properties, and some isotope indicators to characterize and identify these periods, and also include more sites, so we can also picture the regional variability, and then test if our hypothesis that higher dust input occur during warmer times is valid, or we should look for the general picture that in the late Holocene is more complex. So thank you very much.
Thank you, Blas. Very interesting. Do we have questions from the audience? I didn't see any in the chat. Can you tell me what future work you might be doing in these areas?